Hello students, in the previous session we have discussed many trigonometric identities which were true for all values of the angles involved. In this session we intend to discuss those identities where certain relationship exists among the angles involved. Such identities are identities in the sense that they hold for all values of the angles which satisfy the given conditions among them, and hence they are called conditional identities. If A, B and C denotes the angles of a triangle ABC, then the relation A plus B plus C is equal to pi enables us to establish many important identities involving trigonometric ratios of these angles. The following results are useful to obtain the said identities. First, if A plus B plus C is equal to pi, then A plus B is equal to pi minus C, B plus C is equal to pi minus A and C plus A is equal to pi minus B. Second one, if A plus B plus C is equal to pi, then sin of A plus B is equal to sin of pi minus C, that is sin C. Sin of B plus C is equal to sin of pi minus A is equal to sin A, and sin of C plus A is equal to sin pi minus B is equal to sin B. If A plus B plus C is equal to pi, then cos of A plus B is equal to cos of pi minus C, that is equal to minus cos C. Cos of B plus C is equal to cos of pi minus A, that is equal to minus cos A. Cos of C plus A is equal to cos of pi minus B is equal to minus cos B. If A plus B plus C is equal to pi, then tan of A plus B is equal to tan of pi minus C, that is equal to minus tan C. Tan of B plus C is equal to tan of pi minus A, that is equal to minus tan A. Tan of C plus A is equal to tan of pi minus B, that is equal to minus tan B. If A plus B plus C is equal to pi, then A plus B upon 2 is equal to pi upon 2 minus C upon 2. B plus C upon 2 is equal to pi upon 2 minus A upon 2, and similarly C plus A upon 2 is equal to pi upon 2 minus B upon 2. All problems on conditional identities are broadly divided into the following 4 types. Type 1, identities involving sines and cosines of the multiples or submultiples of the angles involved. Type 2, identities involving squares of sines and cosines of the multiples or submultiples of the angles involved. Type 3, identities involving tangents and cotangents of the multiples or submultiples of the angles involved. In the type 4 identities, identities involving cubes and higher powers of the sines and cosines and some mixed identities. We shall now discuss these types of identities one by one. Firstly, let us take up type 1 identities, identities involving sines and cosines of multiples or submultiples of the angles involved. To prove these identities, we use the following algorithm. In step 1, express the sum of first two terms as the product by using one of the following formulae. Sin C plus sin D is equal to 2 sin C plus D upon 2 into cos C minus D upon 2. Same way, sin C minus sin D is equal to 2 sin C minus D upon 2 into cos C plus D by 2. Cos C plus cos D is equal to 2 cos C plus D upon 2 into cos C minus D upon 2. Cos C minus cos D is equal to minus 2 sin C plus D upon 2 into sin c minus d upon 2. In the step 2, in the product obtained in step 1, replace the sum of two angles in terms of the third by using the given relation. In step 3, expand the third term by using one of the following formulae. Sin 2 theta is equal to 2 sin theta cos theta, cos 2 theta is equal to 2 cos square theta minus 1, cos 2 theta is equal to 1 minus 2 sin square theta, etc. In step 4, take the common factor outside. In step 5, express the trigonometric ratio of the angle in terms of the remaining angles. In step 6, use one of the formulas given in step 1 to convert the sum into product. Now, let us solve an example with the help of the algorithm. If a plus b plus c is equal to pi, prove that sin 2a plus sin 2b plus sin 2c is equal to 4 sin a into sin b into sin c. Now, LHS is equal to sin 2a plus sin 2b plus sin 2c. This can be expressed as sin 2a plus sin 2b on clubbing together plus sin 2c. This again using the first step we can express as 2 sin 2a plus 2b upon 2 into cos 2a minus 2b upon 2 plus sin 2c, which could be expressed as 2 sin a plus b into cos a minus b plus sin 2c, and we can express this as 2 into sin pi minus c into cos a minus b plus sin 2c, because a plus b plus c is pi. So, a plus b can be written as pi minus c. Now, 2 sin c into cos a minus b plus 2 sin c into cos c could be expressed as 2 sin c into cos of a minus b plus cos c, and 2 sin c into cos a minus b minus cos of a plus b, because cos of a plus b is equal to cos of pi minus c. This implies cos of a plus b is equal to minus cos c. Using the identity again, 2 sin c into cos a cos b plus sin a sin b minus cos a cos b minus sin a sin b. On opening the brackets, we can simplify this as 2 sin c into cos a cos b plus sin a sin b minus cos a cos b plus sin a sin b. Now, you can see cos a cos b having opposite signs, they get cancelled and we get 2 sin c into 2 sin a sin b, and thus we can write this as 4 into sin a into sin b into sin c, that is nothing but the RHS. Now, let us take up type 2 identities, identities involving squares of sines and cosines of multiples or submultiples of the angles involved. For this, we have an algorithm again. Step 1, arrange the terms on the LHS of the identity so that either sin square a minus sin square b is equal to sin a plus b into sin a minus b, or cos square a minus sin square b is equal to cos a plus b into cos a minus b can be used. In step 2, take the common factor outside. In step 3, express the trigonometric ratios of the single angle inside the bracket into that of the sum of the angles. In step 4, use the formula to convert the sum into product. The following example will illustrate the algorithm. If a plus b plus c is equal to pi, prove that cos square a plus cos square b plus cos square c is equal to 1 minus 2 cos a into cos b into cos c. Taking LHS as cos square a plus cos square b, plus cos square c. We can write this as cos square a plus 1 minus sin square b plus cos square c. Now, clubbing this cos square a and sin square b, we can write as cos square a minus sin square b plus cos square c plus 1. I hope you can follow here. We are using an identity a square minus b square as a plus b into a minus b, and thus we can express cos of a plus b into cos of a minus b plus cos square c plus 1. This again can be written as cos pi minus c into cos of a minus b plus cos square c plus 1. That gives minus cos c into cos a minus b plus cos square c plus 1. Taking minus cos c common, we can write this as cos c into cos of a minus b minus cos c plus 1. This again can be expressed as minus cos c into cos a minus b minus cos pi minus a plus b plus 1 minus cos c into cos a minus b plus cos of a plus b plus 1. On opening the brackets, we can write down this using an identity as minus cos c into cos a cos b plus sin a sin b plus cos a cos b minus sin a sin b plus 1. Again we can see here sin a sin b having opposite signs, they get cancelled, and we get minus cos c into 2 cos a cos b plus 1. That is nothing but 1 minus 2 cos a cos b cos c, that is equal to RHS, hence proved. Now, let us take up one more example. If a plus b plus c is equal to pi, prove that sin square a upon 2 plus sin square b upon 2 minus sin square c upon 2 is equal to 1 minus 2 cos a upon 2 cos b upon 2 into sin c upon 2. Now, considering the LHS as sin square a upon 2 plus sin square b upon 2 minus sin square c upon 2, we can simplify this as sin square a upon 2 plus sin of b upon 2 plus c upon 2 into sin of b upon 2 minus c upon 2. This again can be simplified as sin square a upon 2 plus sin b plus c upon 2 into sin b minus c upon 2, that is equal to sin square a upon 2 plus sin pi minus a upon 2 into sin b minus c upon 2. I hope you understand how I have written b plus c upon 2 as pi minus a upon 2, because a plus b plus c is equal to pi, we are given in the question. That is equal to 1 minus cos square a upon 2 plus cos a upon 2 into sin b minus c upon 2. Now, taking 1 minus cos square a upon 2 minus cos a upon 2 into sin b minus c upon 2, we can express this as 1 minus cos a upon 2. Taking cos a upon 2 common, we could write this as cos a upon 2 minus sin b minus c upon 2. Now, 1 minus cos a upon 2 into cos pi by 2 minus b plus c upon 2 minus sin b minus c upon 2. This could be expressed as 1 minus cos a upon 2 into sin b plus c by 2 minus sin b minus c upon 2. Solving this is equal to 1 minus cos a upon 2 into sin b upon 2 plus c upon 2 minus sin b upon 2 minus c upon 2. Using identity 1 minus cos a upon 2 into sin b upon 2 into cos c upon 2 plus cos b upon 2 into sin c upon 2 minus sin b upon 2 into cos c upon 2 minus cos b upon 2 into sin c upon 2. On opening the brackets, we see here sin b upon 2 into cos c upon 2 get cancelled because they are having opposite signs, and we could express this as 1 minus cos A upon 2 into 2 cos B upon 2 into sin C upon 2. Thus, we can write this as 1 minus 2 cos A upon 2 into cos B upon 2 into sin C upon 2, that is equal to RHS. Now, taking type 3 identities, identities involving tangents and cotangents of the angles involved. We have an algorithm for that. In step 1, express the sum of the two angles in terms of third angle by using the given relation. In step 2, take tangents of both sides. In step 3, expand the LHS in step 2 by using the formula for the tangents of the compound angles. In step 4, use cross multiplication in the expression obtained in step 3. In step 5, arrange the terms as per the requirement in the sum. If the identity involves cotangents, then divide both sides of the identity by the tangents of all angles. Now, let us take up one more example. If a plus b plus c is equal to pi, prove that tan A plus tan B plus tan C is equal to tan A into tan B into tan C. And second one, cot or A cot B plus cot B into cot C is equal to cot C into cot A, that is equal to 1. For the solution, we have A plus B plus C is equal to pi. So, A plus B can be written as pi minus C. Thus, taking tan on both sides, tan of A plus B is equal to tan of pi minus C. This, on using the identity tan A plus tan B upon 1 minus tan A tan B is equal to minus tan C. On cross multiplying, tan A plus tan B is equal to minus tan C plus tan A into tan B into tan C. On rearranging, we have tan A plus tan B plus tan C is equal to tan A into tan B into tan C. For the second part, dividing both sides of the first equation by tan A into tan B into tan C, we get tan A plus tan B plus tan C divided by tan A into tan B into tan C is equal to tan A into tan B into tan C upon tan A into tan B into tan C. This implies 1 upon tan B into tan C plus 1 upon tan C into tan A plus 1 upon tan A into tan B is equal to 1. This again implies cot B into cot C plus cot C into cot A plus cot A into cot B is equal to 1, because cot theta is equal to 1 upon tan theta. We will consider one more example here. Prove that tan x minus y plus tan y minus z plus tan z minus x is equal to tan of x minus y into tan y minus z into tan z minus x. For the solution, let alpha be x minus y, beta be y minus z and gamma be z minus x. Then alpha plus beta plus gamma can be written as x minus y plus y minus z plus z minus x, that is obviously 0. Therefore, tan of alpha plus beta plus gamma is tan 0. This implies tan alpha plus tan beta plus tan gamma minus tan alpha into tan beta into tan gamma divided by 1 minus tan alpha into tan beta minus tan beta into tan gamma minus tan gamma into tan alpha is equal to 0. This again implies tan alpha plus tan beta plus tan gamma is equal to tan alpha into tan beta into tan gamma. This gives us tan of x minus y plus tan of y minus z plus tan of z minus x is equal to tan of x minus y into tan of y minus z into tan of z minus x is equal to RHS. Now, students, there is an assignment for you. Question number 1. if a plus b plus c is equal to pi, prove that cos a plus cos b plus cos c is equal to 1 plus 4 into sin a upon 2 into sin b upon 2 into sin c upon 2. Question number 2. If a plus b plus c is equal to pi, prove that cos square a plus cos square b minus cos square c is equal to 1 minus 2 sin a into sin b into cos c. Question number 3. If a plus b plus c is equal to pi, prove that tan a upon 2 into tan b upon 2 plus tan b upon 2 into tan c upon 2 plus tan c upon 2 into tan a upon 2 is equal to 1. So, students, today you have learned how to solve conditional identities of various types. Thank you.